this is Mrs. Hawk, and I am in my house to show you a little bit about temperature and how that relates to kinetic energy of the particles that are inside the container. And I have three different containers here. I have a very nice warm glass of water, a room temperature or so glass of water, and then one that has some ice inside of it. And way back in the back here, you should be able to see the temperature at 22 degrees Celsius. The temperature on another thermometer right now is reading 19.7 degrees Celsius and about room temperature. So you'll notice some inaccuracy just between the two pieces of equipment. But within that piece of equipment, it should stay pretty close to what the temperature is. And as I move this around inside the container, it still says 22 degrees Celsius. A little leg lamp in there, ice cube just to mark the container so that make the conversation a little bit easier. And I'm going to take this and transfer it over to the warmer container, and you'll notice the temperatures are rising up to 47. And then I do also have some extra water to pour in that is nice and hot. And maybe you can even see, maybe you can't, I can, the steam rising off of it. Not gas being produced, but steam as water vapor. And our temperature has gone up to 55, 56 or so. And if you notice there, it went between the 55 and the 56 and fluttered right around there. What that tells us is that this particular piece of equipment over there measures to the nearest degree Celsius, and it will go between 56 and 55 if it is really close to the middle of 55 and 56, which would be 55.5. So the 5 would round up within the piece of equipment, and 4 and 0.4 and point under, or under 0.4 would go down. So we can get a temperature there, and then I'm going to take it back to this one just to cool it down a little bit and not give it quite the shock. And then move it over here into the ice water, stir it around a bit. Oh, nice. I'm very impressed. And a little conversation here regarding the container and what is being measured. Something to be thoughtful about in this case is that where the thermometer is placed does make a difference. And I'm going to measure from the middle of the container. I did just stir it. I did just stir it with a thermometer too. Yikes, that's not a good idea. And if I have an ice cube here that I place inside, you notice that sometimes there's drips of water that come off of it. Those drips of water are above the freezing point of water, so they're above 0 degrees Celsius. And then as it slips in, we will stir that around just a little bit, see how much it changes. Not much. So in terms of an ice cube, the coldest part of the ice cube is going to be the part that's on the inside of the ice cube. And we really can't get a temperature of the inside of the ice cube without being able to open it up. And then it's no longer the coldest part, because the coldest part would be in the other part. So just a quick little demo there of temperatures. And now a chance to talk about the molecules that are inside of those three glasses, if we're at home, or beakers if they're in the lab. Kinetic energy has to do with the velocity. It also has to do with the mass of the molecules or the particles. The formula for kinetic energy is mv squared divided by 2. We won't be using that. That is a formula that you may have seen in your physical science class, or you'll see in a physics class. And we could even look at calculating the amount of kinetic energy of individual molecules. In this case, we're just going to talk about the relative amount of kinetic energy. And I believe the numbers in the video were 55 degrees was the, I'm going to say, hot container. The room temperature was about 22 degrees Celsius, and the cold container was about 5 degrees Celsius. In order to find out what this is in kelvins, we have to take the degrees Celsius plus 273, and that will tell us the temperature in kelvins. And so real quick, take some time and go do those calculations. There might be a thought process that if we look at this in degrees Celsius, that 5 degrees Celsius is 1/11th of 55 degrees Celsius. If we could consider then that if the degree Celsius temperature is directly related to the amount of energy, that would mean that these particles have 11 times the quantity of energy that the 5 degrees Celsius does. Well, that doesn't really end up to be true. So the Kelvin scale is based off of the idea of kinetic energy as an absolute value. So if you remember, getting down to 0 kelvins is absolute zero, where there are no particles moving at all. So even if we were to take this cold and bring it slower, it will become stopped and they'll just vibrate within their place. And eventually, if we keep making it colder and colder and colder and colder and colder, we can get it down to the point where the electrons aren't even moving. But we're nowhere near that. We'd have 278 kelvins to go. We do get in the wintertime in Minnesota down to where the particles of ice are moving much less than they would if we've got some liquid on it. And skaters are very interested in creating a temperature that is very close to that freezing point. So when we use the Kelvin scale to compare the amount of kinetic energy of the cold with the amount of kinetic energy of the hot water just within this little simulation, there's really not as big of a difference. And I calculated it out, and it is 1.17 times faster, amount of energy compared to here. We could figure out the actual velocity by using the formula up there as well. And if we knew the mass of the particles, which actually we do. But we won't do that for right now. Our conversation is on relative kinetic energy. And so for this purpose, this has low. And in terms of drawing this in for particles, we're talking about H2O. And so it's 1 oxygen and 2 hydrogen. And just for illustration purposes here, vectors are used to diagram the speed of particles, and vectors are with arrows. And so just drawing some arrows that are relatively small on the water molecules shows that these water molecules are moving around within the container. As we move over then to the room temperature, the arrows should get a little bit longer, showing that they are moving a little bit faster, having a little bit more kinetic energy. I don't know, are my particles going fast enough there? And getting over here then to the hot, where the arrows are even longer. So these diagrams now showing the kinetic energy of the particles, and you can pick whatever direction you wanted to go. Notice that there is space in between the particles, and I did that just to show that because I wanted you to be able to see the size of the arrows in the diagrams that I was going to be added on there. But keep in mind that these are liquids, so the particles are actually touching each other. And as liquids, because their speed is what it is between 0 degrees Celsius and 100 degrees Celsius, these are liquids. The particles are attracted to each other. They have, because of their intermolecular forces, the forces are strong enough to hold them together and keep them as a liquid. But if we were to speed them up and get them going faster and faster and get up to 100 degrees Celsius and beyond, then they're going to be turning into gases. So just intermolecular forces as a vocabulary word to also include that. And these are the forces that hold the particles together, particles of water together. All right, skipping down now to a diagram related to the amount of kinetic energy and the number of particles. And I did 3 of them here so that we can take a look at how this diagram will coordinate back up with the ones that are on the top. And if we are taking a look at high kinetic energy, means that these particles would be moving quickly. This would be low kinetic energy. And so, how many of our particles have low kinetic energy? How many of the particles would have a high, super high kinetic energy? There would be some, and I'm just drawing arrows or dots here to show how we might fill this in. If this were like a bar graph where we counted individually and then all of the particles fit in here. So number of particles, a large number are going to have high kinetic energy and low kinetic energy. High kinetic energy over here, lots and lots of them have high kinetic energy and very few have low kinetic energy. So that's a completely filled in bar graph. And then we skip over to I'm going to just go all the way over here to cold, keep kinetic energy on the x-axis, and on the y-axis, I'm going to put number of particles. And this would be a low number of particles a low kinetic energy and a high kinetic energy. So if we're looking at our cold container, there would still be a few over here that have high kinetic energy. And as we go towards the low kinetic energy, now we are finding that there are more and more particles that have low kinetic energy. And to the point, do you want to get a little, get a few in there that are really low kinetic energy. So more of these particles have really low kinetic energy. There are just a few up there that would have a high kinetic energy as well. So number of particles with low kinetic energy is high in the cold container. There are some that have higher. And your temperature is related to the average. And if we look at this diagram right here, this diagram shows that the average would be about here. When we skip over here, now we're looking at the average of all of the particles having a much higher kinetic energy. So this would make it easier for these molecules to escape. So as evaporation were to happen in this particular container, these would be, I'm going to just draw some numbers on here, 3, 2, and 1. 1, 2, and 3. These having low kinetic energy, medium kinetic energy, and then high kinetic energy. And if we slip back up here to this particular diagram, we can equate the same thing, and we can say that this is the number 1 area from the graph down below, where they have the lowest kinetic energy, and then there is the medium kinetic energy, and the highest kinetic energy would be at the top. So as evaporation happens, these fast ones at the top leaving behind particles that are slower. This guy would be leaving as well. You should probably be have more energy over there instead. So I hope that this helps you to have some visualization as to what's happening in terms of the particles inside of the beakers or glasses of water that you might use in your experiment.